for me? Anything from the previous lectures before we start today, the material? Okay, what I wanted, well, you can interrupt me anytime. What I wanted to do is to introduce a few terms that we are going to use in this class, or not necessarily in this as much, but since now we are going into dielectrics, you may see a number of terms as you look at references and so forth, and we would like to know exactly what kind of materials we are going to use in this class. So we know that every dielectric or every material has two important parameters. So far, we've seen one of them, and that is the dielectric constant, all right, or dielectric permittivity, as we call it, but usually we call it, just for simplicity, dielectric constant. So all of the materials have a dielectric constant epsilon, all of the materials, and they have another dielectric constant mu. I'm sure you have seen both of them from physics, all right? So one is epsilon is the dielectric permittivity or dielectric constant, and mu is the magnetic permeability. Okay, now dielectric materials only, not magnetic materials, dielectric materials have mu equals to mu naught. And we have not seen this yet playing in any way, all right? When we go to magnetostatics and eventually electromagnetics, you're gonna see it there all the time. But you need to remember that in terms of mu, it's always mu naught, even if we have not seen it. In terms of epsilon for the dielectric materials, and these are what we have seen so far, we have all kinds of possibilities here. So what we call homogeneous. Homogeneous we call a material where epsilon is a scalar, first of all right? And it has a relative dielectric constant, epsilon sub r, which is this one. And this is constant everywhere. That's why we call it, well, it's a constant because it's a number, but it does not change in the space of interest, all right? And it does not change with time, it does not change with any location in the material, nothing. So that is called a homogeneous material. But so far is the space where, because you can see combinations of these names, as I will say before, later. Homogeneous, therefore, is where epsilon sub r in all of our space of interest is a constant. And of course, epsilon is a scalar. And then you see the relationship between E and D here. Inhomogeneous, of course, is something, is a material where still epsilon is scalar. You still have this relationship here, always. Epsilon is epsilon sub r, epsilon naught. But epsilon sub r, epsilon naught is a constant. We know what it is. It's 8.85 10 to minus 12 farads per meter. It's not going to change, all right? But epsilon sub r can be a function of location in space. So the dielectric can have one epsilon sub r here and another epsilon sub r there, all right? So that is called inhomogeneous. It does not matter how epsilon sub r changes. It can change linearly, can change abruptly, can change like in stepwise, you know, or whatever. But it varies. That is homogeneous. And of course, if that happens, then you can see that D, which is a function of space, of course. Now, the spatial dependence comes from epsilon sub r as well as E. All right, so you see that relationship. Isotropic. You have not heard this before, but you may see it, all right? Isotropic is a material, again, the materials that we have used. Isotropic is a material where E is a scalar. We have that relationship, and we have this. So all of these are, so as you see on the left side, these are all the materials so far, the materials that we have seen. anisotropic, it means that epsilon is not a scalar, but is a tensor. So epsilon means, what is a tensor? It's a matrix that says that, you will see that later, not in this class, but you need to remember that anisotropic epsilon is a tensor, is a matrix, and has 9 elements if we are in 3-dimensional coordinate system. All right, EXX, EXY, and so forth. And why this is important? Because the relationship now in an anisotropic, here I have shown only an epsilon as an example with 3 components. All right, only the XX, YY, and ZZ, but it does not mean that it's only that. Now, this is the important relationship. D is still a vector, E is still a vector, and the relationship now, because epsilon becomes a tensor, is an inner product. The inner product between a tensor and a vector is a vector. Okay, but keep that in mind. We are not going to work with that. Just remember that anisotropic means that epsilon is not a scalar anymore. It's not even a vector. It's something higher in order, all right? It's a matrix. Then the last category, linear. Linear are materials where epsilon is independent of time. All right, there are materials that epsilon changes. For example, you have a paint, all right? You have a glue, for example. You have materials that are in liquid form, very new materials, and then when you let them, they become solids and they become different types of solids. So over time, epsilon changes. That is a non-linear material. Sometimes, like fibers, for example, where you have very high frequencies and when you have optical communications, there are non-linearities that come out of the dependence of the dielectric constant on time. But a linear material, which is like the dielectrics we're going to see in this class, epsilon is independent of time and still has this relationship. And then, of course, the relationship between D and E is the same. Non-linear materials, which are the most difficult to characterize, are ones where epsilon is a function of time. We have not seen that. You're not going to see it in this class. If you go to higher level classes, then if you look at nonlinear optics, if you look, for example, at nonlinear communications, then you will see some materials that have those kinds of properties. So this is just for our vocabulary, all right? So every material we're going to see here is on the left-hand side, on the left column. Materials we're going to see in this class will be homogeneous, isotropic, and linear. So if you want to be accurate, and if I want to accurately say we have this dielectric, I will say we have a homogeneous, isotropic, and linear dielectric. And what it means are all of these the same relationships that you see here. We're not going to do this in this class, of course, but as you go more into electromagnetics, you need to differentiate because all of these other materials are practical. There are materials that you see in hyperspace, all right? There are materials we work with. And therefore, if any of you becomes interested in materials engineering at some point, electrical, but to put more emphasis on the materials, you will see the others as well. So that as an introduction to dielectrics. Now, this is a review. All right, the conduction current. We talked about this, but I want it here, and it is in the book too. And later today, I will give you a list. And I was thinking I will put up there a list because we do specific sections out of the book. So I'm going to start from the beginning, and I'm going to keep adding those sections so you can see them at the top of your of the website. But this is one of the things that you have seen before. I want to review for you. What is a conduction current? All right, and I can say this is convention. I mean, the direction is a conventional direction. Okay, what is a conduction current? Conduction current usually you see in materials that are conducting. This is another type of materials we're seeing in this class. All right, there are conducting materials like a resistor. All right, resistor is a conducting material, always made out of conducting materials. And there are perfect conductors, obviously, where what happens in this, they have another characteristic, sigma. And in these materials, you have free electrons that are ready to go, all right? usually in any conducting material, from perfectly conducting to like some kind of conductivity in there. Perfectly conducting sigma is infinite. You have electrons that have, in perfectly conducting, freedom, they are free to move wherever they go. In lower conductivities, there are not as many, but there are still many electrons that can move. But when do electrons move? They do not move in equilibrium when there is nothing, all right? There is no voltage that is applied to our circuit. There is nothing that excites those electrons. So in equilibrium, the electrons just move randomly, but nothing happens really. But when you apply a voltage here, a voltage V, okay, there, V, practically, what you do is that you have a supply of positive charges on the left of your voltage, where there are show plus, and then you have a supply of negative charges on the right. When the electrons inside these conductors see the positive charges, of course, they are going to flow, all right, to neutralize them, and they flow to the left. However, if the electrons flow to the left, then they leave holes behind them. Therefore, the movement of electrons to the left is simulated by a movement of holes to the right. All right. So every time an electron moves to the left, there is a hole that moves to the right. I mean, this is like the visual thing. If you were to go on, like, create a video where you have an electron and everything is in equilibrium, and then this electron starts moving, another electron fill the position, you see the hole moving like that. Even in reality, it's only the electron that's moving. All right, a hole, the movement of the hole does not show anything else, but it shows how the lack of an electron, it shows in space. Okay, so the convention that we are using, even if electrons truly move to the left and towards the positive pole of the battery, we consider the flow of the current to the right. So in our circuits, always, we show flow of current from the plus pole of the battery to the negative. But that's the convention we use. And on the basis of that convention, we write all of the circuits, all of the circuit expressions, all right? We write Ohm's law, Kirchhoff's laws, whatever. We have built the whole circuit theory on that. So you need to remember it. Electrons to the left, but the conventional current shows to the right. And the current density of that current, the total current, of course, is made out of infinitesimally thin currents. And each one of these filaments, all right, which is in your mind, you should consider like an infinite long, not quite infinite in this case, but a very thin line that goes from one end of the conductor to the other. You have many multiples like that. So practically, it's like those filaments send electrons in parallel. So practically, you think that the electrons go like one after behind the other, all right? And you have multiples like this, all right? So a current density is a function of the electric field intensity through this expression. All right, the current density, we'll see more of that later, but now to introduce it, current density is sigma, which is the conductivity, times the electric field intensity. And that's the current density. But the total current, you will have to integrate the current density over the cross-section of the conductor. All right, because practically you think that if this is the cross-section of a conductor, all right, let's assume that this is a conductor, that the currents flow like this. All right, you have a lot of filaments that make the total current, and each one of them is a current density, but the total current will be the surface integral of this current density on the surface, the cross-section of the conductor. All right, we'll see this again, but now we just introduced the conduction current. Okay, We've done that now. And we are going to introduce a new set of conditions since we are going back to dielectrics. Since now we are going to start using dielectrics more, all right, in our thinking. So far we had charges in free space. You saw an example in the homework that I gave you that was a dielectric with charges, as opposed to being free space, charged sphere, if you like, uniformly charged sphere. In class, we did it only the charges were in free space when they made the charge sphere. In the homework, the charge sphere had a dielectric, the material had a dielectric constant. However, and that was easier because we have solved the problem, all right? However, when you do have dielectrics and you try to solve a problem using dielectrics, as you will see after we cover also capacitance, we'll go to coaxial lines, then you see that you have to know exactly how an electric field behaves when you are in an air dielectric interface. And there is a very extensive calculation that leads to these two types of equations, but I will skip that. I'm sure that if you go to, even if we cover it, you're not going to remember it after that. So if you go to higher level class, you're going to do it again. All right, and you're going to do it because you're going to learn techniques on how to calculate those things. But now you just need to remember two things. If we have air on top, E1, D1, that's how we characterize the electric field. And what is D1? Just so we remember. D1 is epsilon naught, because this is air, and this is the dielectric. All right, and we have D1 is equal to epsilon naught E1 here. While inside the dielectric, we have the D2 is equal to epsilon, which is epsilon R, epsilon naught E2, or epsilon R, epsilon naught E2. And since I'm writing this expression, what kind of a material, of a dielectric material I have considered, is isotropic, all right, is linear, and it's homogeneous. We don't say all of this, but that's what the type of material we have. Okay. Now, when we have a planar interface, here, as you can see, I have attached to it the Cartesian coordinate system. X comes out of the wall, X comes out like that. Y goes to the right, and then Z goes upward to create a positively defined or counterclockwise defined coordinate system. This is how we do it. And therefore, because I have done it like that, instead of saying I have three separate components of the electric field and therefore of the electric flux density, I say that I have two types of components. A perpendicular that goes along the Z direction, and I show it with this. With the perpendicular, we show it like that. All right, that is a perpendicular. And that means that for a planar interface is that perpendicular direction. Whatever that direction is, my case is Z, but it's the perpendicular. And then I have another type of a component, which I call the parallel. And the parallel means parallel to the interface. It could be either EX or EY. All right, so parallel here, which means parallel to the interface. All right, always interface here. And the same here. All right, so what do conditions, boundary, what we call boundary conditions, what do they say? They say the following. These two, I will show it here. If you have an electric field, the perpendicular components of the flux density are equal through the interface. Flux density. The perpendicular components of the flux density are equal through the interface. And that's what I say here. all right, in this one, flux density. And the parallel components of the electric field are continuous through the interface. And that's what I say here. All right, these are the two important conditions. When it comes to the perpendicular component, is the electric flux density is D that is continuous through the interface. Which means what about E? If D is continuous through the interface, if this is D perpendicular 1, and if this is D perpendicular 2, these two are the same at the interface. If they are continuous, they have to be at the interface, they have to be equal. If those are equal, are continuous to the interface, what happens to the perpendicular electric field? Is it also continuous through the interface or not? You need to remember the relationship between D and E. And you need to remember that the upper part is air, the lower part is dielectric. It could be one dielectric with another dielectric, for example. So what happens to the parallel components, to the perpendicular components of the electric field through the planar interface between two dielectrics? Is it continuous? Exactly, so they are discontinuous. The perpendicular electric field is discontinuous because it's the D field that is continuous. Okay, why should that make sense to you? I'll tell you why it should make sense. Do you remember Gauss's law? What does Gauss's law say? Gauss's law in the simplest, Gauss's law says this, equals Q, all right? If my field were to vary only along the Z direction, all right, so here is dielectric. Let's assume that my field varies only along the Z direction, okay, for a moment. And that this is air, and this is epsilon, the dielectric, which is that. Let's assume for a moment that D is only a function of Z. Then what does this give? This will give dz, all right, equals Q. If I take one point here above and one point here below, and I bring these points very close to the interface, let's assume that this will be a distance delta Z, all right? How do I write the derivative? I write the derivative as delta of D delta Z equals Q, which means that D in the point, say what I'm calling point A here, A, and point B. That means that D at point A minus, that's the delta D, minus D and point B at point B divided by delta Z equals Q, which means that shows something very interesting. It shows that for the two deltas, which are, as I said, along the z direction, all right? So let me write it here. Z, write it. AZ, let's write like that. So here, let me see, B, that says that these two are equal to Q delta Z. So unless you have Q accumulated on the surface of the dielectric, somebody forces it then to be, the two Ds are equal through the interface. Otherwise, if they were not equal, then that tells you that there is a Q accumulated at the interface, all right? That's why it is this formulation, and therefore, if Q does not accumulate on the interface, that means that dA equals to dB. So practically, I mean, I have reduced the problem to one dimension to help you, right? So practically, you need to remember, so this is explanation. 1D. To remember that when you have an air dielectric interface, the normal planar, the perpendicular components of D are equal, but the parallel components of V are equal through the interface, are continuous through the interface. Okay, any questions? We are going to use this quite a bit in the following. So I need to set it up there. We call them boundary conditions. So I would say if I have an air dielectric interface and I tell me your the boundary conditions, you have to show me these two boxes. You have to show me this and that. If I ever ask you in a test, in an exercise, in a homework, write the boundary conditions, how they apply, you're gonna show me these two. In the same way they apply in cylindrical coordinates or in spherical. But we are going to do that because you understand in a spherical coordinate, when you go on the surface, the perpendicular component is along the radius, is the radial component, all right, on a spherical surface or on a cylindrical. But the horizontal are the ones that are tangential to the surface. The parallel, I should say, are the ones who are tangential to the surface, all right? So we are going to see it later. The conditions will not change if we go from a planar coordinate system to a cylindrical and then to a spherical. And that's why I like to write them as perpendicular and parallel, because the coordinate systems change, and I did not want to, and those remain, as long as you can understand what are your perpendicular components in all three coordinate systems, all right? And what are the parallel to the surface components in all three coordinate systems. Okay, so we're going to see them again, but remember them, these are the boundary conditions. Any questions so far? Okay, so now we are talking about capacitance. And how we are going to try to go to capacitance? We are going to start with something that we've done in the past. So let's assume that I take the following out. So here is how I'm going to do that. Let me see. I don't want to lose anything there, of course. So let me take this. Okay, so I copy it and then I cut it. Cut. Okay. We solved this problem when we had a charge on the surface of a perfect conductor. You remember that? What did we find when we had a uniform planar infinite charge? What did we find about the field? Do you remember? Exactly. We found that the field does not change. So here, how would the field go here? These are negative charges. So how does the field go to a negative charge? If say you had positive charge somewhere else, it would go towards the negative charge. You remember that? Usually if you have a negative charge, like this one that I have here, the field to this will go like that, if it was by itself. And if I have a positive charge, like this, I would write the field always like this, okay? So having that in mind, how would I write the constant field here? I will write it as follows. Here, here, all right? Now, what happens if I keep this lower perfect conductor with the negative charges, and then I bring on top of this another conductor with the same positive charges? What would happen to the field? I would have the parallel surface of the perfect conductor here. And I would have these positive charges there. So it will be all of those. Yeah, let me write them first. Do them like this. And there will be positive charges. It means I would have here. What would this do? They will create their own field. How would that field look like? It will look like this. Do you agree? So the two charges that face each other, they contribute their own fields. And if the charge density on both sides, and these are infinite surfaces, is the same, then what happens? The fields are identical because the field only depends on the charge density. You remember from what we solved the problem of a charge density on an infinite plane? The field was equal to the charge density divided by 2. So practically, if here we have a charge density, QS, surface charge density, and then it's negative, negative, and then here we have a positive, same positive charge density, then E, the negative one, would be, all right, would have been, now I took already the direction into account, all right, so I'm not gonna have the negative in the E field, but it's gonna be, because I have the direction, QS is like going toward, it's gonna be QS over 2, and the positive is gonna be how much? QS over 2. So then if you sum them up, because they have the same direction because of the negative charge underneath, because it has the other direction of the lines, positive charge on top, what is gonna be the total field? QS. You agree, you see that? Practically, we have the problem of the infinite plane with charges equally distributed. But here we have 2 of those, so we use superposition. And then it happens because the charges are positive and negative that the electric fields, what do? They add. They add up. Okay, so let me take this away now, since I explained it, and I will put back what I had before. So okay. So how now, what I did is we have exactly what we had before, but now I have made that happen through a battery. That's what we normally do, right? If we have, this is like a capacitor practically. Even if I show an infinite plane underneath it conducting an infinite on top, they are never infinite. They are two thick plates. All right. And then what we do, we put a battery that we connected with the two plates of the capacitor. And that battery gives a positive charge that distributes evenly because it's an infinite plate, a negative to the top, a negative charge to the bottom that it distributes evenly. And that therefore creates an electric field inside between the two plates of the capacitor, which is equal to QS over epsilon naught. Question for you. What happens if, of course, you cannot keep two plates like this in air. So always capacitors have what in between the plates? They have dielectric, and they have a dielectric because they want the two plates to be at equal distance. And how do you hold two metallic plates in equal distance? By placing another material in between, and they place a material that does not have losses, so dielectric. So practically in here, you're gonna have, you're gonna have here a dielectric, all right, which is gonna fill this space. And if this dielectric has, of course, is not air, so it's gonna have an epsilon, and this epsilon is gonna be homogeneous and isotropic and the whole good thing, all the good properties. And if in this case, epsilon inside here is epsilon r, let me write it smaller. If epsilon here is epsilon r, epsilon naught, then this one here is gonna be epsilon, which is epsilon r, epsilon naught, all right? So far so good. So now we have established the kind of field we are gonna have. Now we go to something more practical. We say, okay, let us now assume that we do have two plates, like we normally have in a conductor, all right? And for a moment, I will assume that this is air, but now, as you know, we can put any dielectric in between, all right? Can really put any dielectric in between these two. And as a matter of fact, I could do it here and put a dielectric in between, like here. Okay, so since we have a dielectric, well, just our formulas here are gonna have, instead of epsilon naught, they're gonna have epsilon. So that's the only difference. All right. So then we have the field, all right? And we have the voltage that applies between the two plates. It's VD. What is the relationship between the voltage and the field between the two plates? Is this one. If you remember from the potential tells us that the voltage VD is the line integral from 1 to 2. Okay, VD is positive at 1. So from 1 to 2 of the electric field, all right? 1 to 2 of the electric field. Therefore, is gonna be the negative of from 1 to 2, which means here, as you can see in this expression, it was gonna be, I can move this a little further. It was gonna be minus V2 minus V1, but V2 is negative, V1 is positive. So practically, that gives us that to be V1 minus V2, which is V sub D, which is Q sub S over epsilon H, because now we have a dielectric in there. All right. Now, what else do we know? We know that there is, since it's a finite conductor, both on top and below, we have a total Q. And because Q is distributed evenly throughout the conductor, we have that the total Q is going to be the surface charge density multiplied by the surface of the conductor, all right, for the positive, and the same thing for the negative side. And therefore, I'm going to have here that V sub D is going to be, I will take this equation and this equation, and I will combine them. And therefore, I have that V sub D is equal to Q over epsilon AB, and all of this times H. And AB is the area. So I have an epsilon times the area. Okay. And, sorry. All right, which practically then gives me V sub D in terms of Q, the geometry of the capacitor, and the dielectric constant of the material. Now, I introduce a new concept, which I call the capacitance for this structure. And therefore, we call that structure the capacitor. And capacitance is Q over, all right, the Q that applies on one plane divided by the voltage that applies. And therefore, see from here, C, capacitance, comes to be a quantity, an electrical quantity that only depends on the geometry of this capacitor and on the dielectric constant of the material. And it's this one. And that's why do we develop this? Because this is equivalent if I were to take this distributed structure and make it into a circuit, that above distributed structure here will be equivalent to one capacitor connected to the voltage source. All right. So practically, we replace all of these 3D with one circuit element, which we call the capacitor. Okay. Any questions about this so far? These are things that you have seen before. Okay, what will you do next? We are going to start doing a lot of different things. First of all, changing the material inside the capacitor. We'll do that next time. Changing the material to have more than one materials. Some of them will be lined perpendicular, one next to the other, like in columns, and the other is going to be like slabs, one on top of the other. So we'll learn how without solving the problem again, we'll be able to find the total capacitance. Then we are going to start connecting structures like this. We would like to see what happens if we apply a voltage to one side, but we leave the other disconnected. What's going to happen to that capacitance? It's going to be the same, it's going to be different. These are very practical problems, all right, that you see in circuit design. If you don't ground one side of the capacitor, then it's not performing for you because it gives you something different. It's not the capacitance that we calculate from here. All right, or if you have capacitors one next to the other or parallel. How did we get the formulas for series capacitances and parallel from here? Nobody told you that, but in reality, that's how you got the formulas that we used in circuit design. All right, if you have two capacitors in series, what happens? Is the capacitance bigger or smaller? smaller. If they're in parallel, bigger. How does this come out? We are going to see it from here, all right? It all has to do with the fields that you excite there. All right, any questions about it? All right, so I'm going to assign to you. Let me see what I'm going to assign. 1 second. All right. I'm going to assign exercise 7, which is called the capacitor. And you're going to have until Wednesday to do it. All right? It's exercise 7, and it's called the capacitor. So obviously we are jumping. I had a whole list of exercises, all right? I'm not giving you everything, but this is what we have for Wednesday. Okay, thank you.